high-performance dynamic CMOS circuits. The circuits presented here are variants of the basic dynamic CMOS logic gate structure. We will see that they are designed to take full advantage of the obvious benefits of dynamic operation and at the same time to allow unrestricted cascading of multiple stages. The ultimate goal is to achieve reliable high-speed compact circuits using the least complicated clocking scheme possible. Dynamo CMOS logic. Consider the generalized circuit diagram of a dynamo CMOS logic gate shown in figure. A dynamic CMOS logic stage such as one shown in figure is, you can see the figure, generalized circuit diagram of a dynamo CMOS logic gate. You can see the figure, cascaded dynamo CMOS logic gates. Cascaded with a static CMOS inverter stage, the addition of the inverter allows us to operate a number of such structures in cascade, as explained in the following. During the pre-charge phase, when Ck equal to 0, the output node of the dynamic CMOS stage is pre-charged to a high logic level, and the output of the CMOS inverter buffer becomes low. When the clock signal rises at the beginning of the evaluation phase, there are two possibilities. The output node of the dynamic CMOS stage is either discharged to a low level through the NMOS circuitry 1 to 0 transition, or it remains high. Consequently, the inverter output voltage can also make at most of one transition during evaluation phase from 0 to 1, regardless of the input voltages applied to the dynamic CMOS stage. It is not possible for the buffer output to make a 1 to 0 transition during the evaluation phase. Remember that the problem in cascading conventional dynamic CMOS stages occurs when one or more inputs of a stage make a 1 to 0 transition during the evaluation phase, as illustrated in figure. On the other hand, if we build a system by cascading dynamo CMOS logic gates as shown in figure, all input transistors in subsequent logic blocks will be turned off during the pre-charge phase. Hence, since all buffer outputs are equal to 0 during the evaluation phase, each buffer output can make at most one transition from 0 to 1, and thus each input of all subsequent logic stages can make at most one 0 to 1 transition. In a cascade structure consisting of several such stages, the evaluation of each stage ripples the next stage evaluation, similar to a chain of dynamos falling one after the other. The structure is hence called domino CMOS logic. Domino CMOS logic gates allow a significant reduction in the number of transistors required to realize any complex Boolean function. The implementation of the 8-input Boolean function Z equals to AB plus C plus D E plus F and GH using standard CMOS and domino CMOS is shown in figure. Here the reduction of circuit complexity is obvious. the disturbance, the distribution of the clock signal within the system is quite straightforward. This is figure A, this is figure B. Figure A, 8 input complex logic gate realized using conventional CMOS logic, and B, dynamo CMOS logic. Straightforward. Since a single clock can be used to pre-charge and evaluate any number of cascaded stages as long as the signal propagation delay from the first stage to the last stage does not exceed the time span of the evaluation phase. Also, conventional static CMOS logic gates can be used together with the domino CMOS gates in a cascaded configuration figure. The limitation is that the number of converting static logic stages in cascade must be even, so that the inputs of the next domino CMOS stage experience only 0 to 1 transition during the evaluation. Here you can see the figure cascading domino CMOS logic gates with static CMOS logic gates. There are also some other limitations associated with domino CMOS logic gates. First, only non-inverting structures can be implemented using domino CMOS. If necessary, inversion must be carried out using conventional CMOS logic. Also, charge sharing between the dynamic stage output node and the intermediate nodes of the NMOS logic block during the evaluation phase may cause erroneous outputs, as will be explained in the following. Consider the domino CMOS logic gate shown in figure, in which the intermediate node capacitance C2 is comparable in size to the output node capacitance C1. We will assume that all inputs are low initially and that the intermediate node voltage across C2 has initial value of 0 volts. During the pre-charge phase, the output node capacitance C1 is charged up to its logic high level of VDD through the PMOS transistor. In the next phase, the clock signal becomes high and the evaluation begins. If the input signal of the uppermost NMOS transistor switches from low to high during this evaluation phase, as shown in figure, the charge initially stored in the output capacitance C1 will now be sharing by C2, leading to the so-called charge sharing phenomenon. The output node voltage after charge sharing becomes VDD by 1 plus C2 by C1. For example, if C1 equals C2, the output voltage becomes VDD by 2 in the evaluation phase, unless its logic threshold voltage is less than VDD by 2. The output voltage of the following inverter will then inadvertently switch high, which is a logic error. Thus, it is important to have C2 much smaller than C1. Several measures can be taken in order to prevent erroneous output levels due to charge sharing in domino CMOS gates. One example solution is to add a weak PMOS pull-up device with a small WL ratio to the dynamic CMOS stage output, with which which essentially forces a high output level unless there is a strong pull down path between the output and the ground. It can be observed that the weak PMOS transistor will be turned on when the percentage node voltage is kept high. Otherwise it will be turned off as Vout becomes high. Here you can see the figure. Charge sharing between the output capacitance C1 and an intermediate node capacitance C2 during the evaluation cycle may reduce the output node voltage level. In this figure, a weak PMOS pull-up device in a feedback loop can be used to prevent the loss of output voltage level due to the charge sharing. Another solution is to use separate PMOS transistors to pre-charge all intermediate nodes in the NMOS pull-down tree which have a large parasitic capacitance. The pre-charging of all high capacitance nodes with the circuit effectively eliminates all potential charge sharing problems during evaluation. However, it can also cause additional delay time since the NMOS logic tree now has to drain a larger charge in order to pull down the node voltage Vx. Another way of preventing logic errors due to charge sharing is to make the logic threshold voltage of the inverter smaller, such that the final stage output is not affected by lowering of Vx due to charge sharing. It should be noted that his design approach would trade off the pull-up speed weaker PMOS transistor for lower sensitivity to the charge sharing problem. The use of multiple pre-charged transistors also enables us to use the pre-charged intermediate nodes as resources for additional outputs. These additional logic functions can be realized by tapping the internal nodes of the dynamic CMOS stage, as illustrated by two series connected logic blocks in figure. The resulting multiple output domino CMOS logic gate allows us to simultaneously realize several complex functions using a small number of transistors. Figure shows the realization of. Here you can see the figure. Pre-charging of internal nodes to prevent charge sharing also allows implementation of multiple output domino CMOS structures. Figure example of multiple output domino CMOS gate realizing four functions. Four Boolean functions of 9 variables using a single domino CMOS logic gate. The four functions to be realized are listed in the following: C equal to G1 equal to P1 C0, C2 equal to G2 plus P2 G1 plus P2 P1 C0, C3 equal to G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 C0, C4 equal to G4 plus P4 G3 plus P4 P3 G2 plus P4 P3 P2 G1 plus P4 P3 P2 P1 C0. It can be shown that the functions C1 through C4 are the four carrier terms to be used in a four-stage carry look ahead carrier where the variables G, I and Pi are defined as Gi equal to Ai into Bi, Pi equal to Ai plus Bi, and Ai, Bi are the input bits associated with the ith stage. Hence, this circuit is also known as Manchester carry chain. The generation of the 4 carry terms using 4 separate standard CMOS logic gates or 4 separate single output domino CMOS circuits, on the other hand, would require a large number of transistors and consequently a much larger silicon area. Variants of the multiple output dynamic CMOS circuit shown in figure are used widely in high performance adder structures. Here you can see the figure. A 4 input domino CMOS NAND gate, and B the corresponding stick layout to show the graded scaling of NMOS transistor sizes for improving the transient performance. The transient performance of domino CMOS logic gates can be improved by adjusting the NMOS transistor sizes in the pull-down path with the objective of reducing the discharge time. Soji has shown that the best performance is obtained with a graded sizing of NMOS transistors in series structures, where the NMOS transistor closest to the output node also has the smallest WL ratio. The domino CMOS circuit diagram and the corresponding stick diagram layout of an optimized example are shown in figure. The fact that a graded reduction of transistor sizes from bottom to top ultimately leads to a better transient performance may seem counterintuitive, but this effect can be explained by observing the RC delay of the combined pull-down path consisting of series connected NMOS transistors. Consider first NMOS transistor closest to the output node. If the WL ratio of the transistor is reduced by a certain factor, two effects occur. The first, the current driving capacity will decrease, that is equivalent resistance of the NMOS transistor will increase. Second, the parasitic drain capacitance associated with this transistor will decrease. If the length of the NMOS chain is sufficiently long, the increase in resistance has little influence upon the combined RC delay time, whereas a reduction of capacitance significantly decreases the delay. In fact, by applying Elmore's RC delay formula, see chapter 6, to series connected NMOS structures, one can determine if a reduction of NMOS transistor sizes will improve a transient performance. Let CL represent the pre-charge node load capacitance of the domino CMOS gate, and let C1 represent the parasitic drain capacitance of the NMOS transistor closest to the pre-charge node. It is assumed that the inverter transistor sizes are fixed and that the pull-down chain contains N series connected NMOS transistors. Soji has shown in that if the following condition CL less than n-1 C1 by 2 is satisfied, the overall delay time can be reduced by decreasing the size of the NMOS transistor closest to the output node. This result can be iteratively applied to the other transistors in the pull-down chain, which leads to graded sizing of all NMOS devices. On the other hand, if the inverter gate transistors are allowed to be optimized along with the series connected transistors. Even shorter delays can be achieved with the smaller chip area. Thank you.